Okay, so we just started looking at graphing sine and cosine functions. And so let's continue to work with that. And so we were looking at the form when y is equal to, or f of x, a times cosine of bx, and y is equal to a sine of bx. So when we have this, our amplitude was equal to the absolute value of a. And then our period, so we just started talking about this yesterday, how to find that if this was not just x in here. And so our period is equal to basically what you're doing. A normal period for sine and cosine is sandwiched between 0 and 2 pi. And so here we're going to put that argument, theta is normally between that, so we're going to put bx is between 0 and 2 pi, including. Divide both sides by b to get x by itself. Well, we get 0 divided by b is less than or equal to x is less than or equal to 2 pi divided by b. So this is 0 is less than or equal to x is less than or equal to 2 pi over b. Well, if I'm looking at the length of that interval starting at 0 and going to 2 pi over b, my period, that length, is 2 pi over b. So our period, and you can always find it by doing this like this, is 2 pi over b. So when you're graphing these, the best thing to do is first, let's find our period. And so depending on if we're a sine function or cosine function depends on where we're starting. So we had saw that yesterday that our cosine function, that one started when x was 0 at 1, and then it came back down, hit the x-axis at pi halves, and then at pi it hit -1, came back up. So these are kind of important points. Where if we looked at the sine function started at the origin and then increased and came down and up. So depending on what function we are, depends on, are we going to start at 1 or the amplitude, a or negative a, or are we going to start at the origin? So first we're going to find the period, then we're going to split the period, or one period, into the start value, the quarter value, the half value, the 3/4 value, and the endpoint. And so those are all important points. Those were either points where it was going to either hit a max or a min on the sine or cosine curve, and it was points where it was going to cross the x-axis. And so if we could find these values for what our period is, then it's going to be pretty easy to plot. And so plot your max, min, and x-intercepts. By the numbers found in part 2. And then we can graph. So let's look at one. So if we had y is equal to -2 sine of 1/2 x. Oops. Probably in here I should have put in determine the amplitude, because max and mins are based off of the amplitude. So maybe on part 3 using the amplitude, also using amplitude. Okay, so what affects the period is what is called the argument, that 1/2 x. And we want to sandwich that in between our 0 and 2 pi. And so doing that, we have 0 is less than or equal to 1/2 x, which is less than or equal to pi, 2 pi. So we want to get x by itself. And so in order to do that with a compound inequality, we can multiply all sides of the inequality by 2 to clear that fraction. And so doing that, well, 0 times 2 is 0, is less than or equal to, this is going to just give me x, is less than or equal to 2 times 2 pi is 4 pi. So that actually is a nice one. So our period is 4 pi. Our start value, we're starting at 0. Our end value, oh, let's just write quarter, 1/2, 3/4, and end. Well, our length is 4 pi, and we're starting at 0, and so our end value is 4 pi of 1 period. And so halfway mark of 0 and 4 pi, well, halfway is 2 pi. So to get the quarter point, that's a halfway between the 0 and the halfway point. Well, 0 and 2 pi, half of that is just 1 pi, or pi. And then if I was looking at the halfway point between 2 pi and 4 pi, that is 3 pi. Okay, so let me just kind of put that in there so that you can recall to find the halfway. Way mark. Start plus end divided by 2, but sometimes because we're dealing with fractions, it's easier to think of it as multiplying by 1/2, same thing. So 2 pi plus 4 pi is 6 pi. 6 pi divided by 2 gives me the 3 pi, the halfway mark between 1/2 and end. Okay. So we figured out our important points. Our amplitude this is equal to the absolute value of A. A is that coefficient in front of the sign. And so the absolute value of -2 is +2. So I know I'm going to have a max at 2 and a min at -2.
Professor, what does it say after where you put the note recall to find halfway? What does it say? Mark?
Mark, yeah. So to find the halfway mark, it's going to be equal to half times the start plus the end point that you're trying to find the halfway between. Okay, so let's plot those important points on the x and the y-axis. So we have 0, we have pi, we have 2 pi, we have 3 pi, and we have 4 pi. We can go further if we want. But for now, let's just worry about those. And then our amplitude, we said was 2 and -2, or was 2, but our max and min is determined by that. Okay, so depending on if we're a sine or a cosine function depends on if we're starting at the origin or above or below the x-axis. This negative sign in front of the 2, this is making it a reflection. So this reflects just 2 sine of 1/2 x across the x-axis. Transformations of graphs. This is a sine function. Sine normally starts at the origin, and we didn't have any vertical shifts. We're not doing that yet. And so I'm going to start at the origin. I know my start point is 0, and I'm starting at the origin here. So 0, 0. But instead of hitting my max at pi, I'm going the opposite direction because of that negative. So at pi, I'm going to hit my min, which is -2. I have to turn around, come back, hit the x-axis. So 3 pi, I'm going to hit 2. 4 pi, come back around and hit the x-axis. And I can continue that pattern every pi. I'm either going to be hitting a max, min, or the x-axis. And we got the picture. So I'm not exactly sure how my math lab does it on this. I know the other program or other book I used with my math lab, I believe you chose, they gave you, multiple choice on which graph. The thing is that normally I don't have multiple choice. I want you guys to be able to graph this without, looking at which one you think it is. You should be able to go through that process and graph it. So when you're showing your work, graph it, and then go find which graph it looks like on my math lab.
Professor, I had a question.
Yes.
So because it was negative, we plotted the first point after 0, 0 below the x-axis, right?
Right, exactly.
Okay. I just wanted
Exactly. So just because of that negative out front of that sine function, we had to head the opposite direction that we would have if that negative hadn't been there.
Excuse me, I had a question as well.
Yes.
So, if we're like unsure about where to put the y coordinate, can we just plug in the x value into the equation to get the y?
You can definitely. It's just sometimes harder to see, but you could plug in 0 in there for x, and we would have -2 times sine of 0. Well, sine of 0 is at 0, and so 0 times that -2 is 0. So you would see that that point is 0, 0. And then you could plug in pi in here and look at what is sine of pi halves. Sine of pi halves, so that's 90 degrees is 1. And so 1 times the -2 in front of our sine function gives us -2. But this kind of gives us a way that we don't have to go through and plug in those numbers to figure out those sine functions. And sometimes it's harder because they're not exactly the ones that we know what they are. Okay, so let's maybe look at another one. So if we had Oh, they are throwing it at you. Okay, great. Let's say you had y is equal to 3 sine of 2x. Okay, so we want to find our period. Sandwich the argument between 0 and 2 pi and get x by itself. So to get x by itself in between in this inequality, compound inequality, we would divide through everything by 2. Well, 0 divided by 2 is 0. Is less than or equal to x is less than or equal to pi. So here we have our period is pi. So we know our start value is 0. We're going to find our quarter, we're going to find our halfway mark, we're going to find our 3/4 point, and our end value. We just found the end value, that was pi. So if we sum these two and divide by 2, or multiply by 1/2, so 0 plus pi is pi, pi times 1/2 is pi halves. You probably could see that that was a halfway mark. 0 plus pi halves is pi halves times 1/2 is pi fourths. And pi halves plus pi, all times 1/2, doesn't matter if it's in front or in the back. Well, I need a common denominator to do this. So this is really 2 pi over 2. So this is 3 pi halves times 1/2 is 3 pi fourths. So you might have been able to look at this without going through and summing the end or the start and the end value to get the halfway point. But there are times where it's hard to figure that out without going through this process. So we got our period, we got it broken up so that we can plot this. Our amplitude, that's the absolute value of A. Well, the absolute value of 3 is 3. So I know a max is going to hit at 3 and a min is going to hit at -3. And so I would plot my important points for one period. And it really doesn't matter how wide you make your units. So I tend to make them the same just because it's easier to graph. But basically this is going to be squished further than the normal sine function. So it's going to repeat faster, where the last one, it was taking a slower time to complete a period, that 4 pi. Okay, so we have 0, pi fourths, pi halves, 3 pi halves, sorry, 3 pi fourths, and pi. We know max, we're going to go up 3, and we're going to go down -3. So I determine which trig function I'm using. I'm using sine, so I know sine starts at the origin. And then I need to determine which direction I'm going. The coefficient in front of my sine is positive, so I'm going to increase first. So pi fourths is where I'm going to hit my maximum. Pi halves, I'm going to hit my x-axis. 3 pi fourths, I hit my -3. Pi, come back and hit the x-axis. So that's just one period of the graph, but that goes on infinitely.
Excuse me, Professor?
Yes.
So if it was cosine instead of sine in this example, would the first point be 0, 3?
Yes, you're right. Good job. So maybe we should just plot that real quick because we did most of the work already. So if this was y is equal to 3 cosine of x, or cosine of, what was it, 2x? Yeah. We still have our important points that pi fourths, we have the pi halves, the 3 pi fourths, and the pi. We still have our amplitude is 3, so max and min is 3 and -3. But like you said, this is a cosine function, so instead of the origin, we're going to either start at the max or the min, and it depends on is that coefficient in front of the cosine positive or negative. Since it's positive, we're going to start at the max of 3. We're going to come down to the quarter point and hit the x-axis. Halfway point of the period, we're going to come down and hit the -3, come back up, hit the x-axis, and then hit +3. So knowing this little step of, figuring out what the period is and then breaking it down like that, like I said, it just makes it so much easier to graph. And then using a little bit of rules of transformations of graphs are helpful. Like that negative in front of the trig function is a reflection across the x-axis. So there's one other thing that you need to, or a couple other things you need to remember with transformations of graphs. So recall, if you have some function f of x and you add a constant to that, or you subtract a constant to that, this shifts the graph. That plus k, that constant, this shifts the graph of f of x. Up k units. K is bigger than 0. And down k units. If k is less than 0. So if you subtract a number from your function, we're going to shift everything down that number of units. So when we're doing this, we're going to treat that number of units that we're shifting up or down. We're going to look at that with our x-axis. So we're going to treat that x-axis, or we're going to call it the midway line. So our midway line is where our x-axis normally was for our amplitude. But when we shift things up or down, when we're graphing it, that's where it's going to be what we're going to think of as crossing the x-axis or the midpoint line. So for instance, let's see. Going out. Let's say you had y is equal to -3 cosine of pi fourths x plus 2. Okay, so that plus 2 outside, this is telling me that we're shifting the graph up 2 units. So where our x-axis would be, that which was normally our midway line, it's now shifted up 2 units. So that's what I call it. I'm not sure if that book calls it this, but our midway line is the horizontal line y equals 2. The -3, well, that helps us with the amplitude. So amplitude,
Excuse me, Professor?
yeah.
So does that mean the midway line is whatever the graph is shifting up or down?
Yeah, so that's where, when we're looking at our trig function, that's where it's going to be touching. Instead of where it would have been touching the x-axis, it's going to be touching that midway line instead. I think once we do it,
Yes.
maybe that will help. Oops, and I didn't mean to put the absolute value of -a, which is the same thing, but absolute value of a is 3.
Professor,
Yes.
I don't mean to confuse anybody else, but if you add outside of the parentheses, it's going to be a vertical shift, and if you add within the parentheses, it's going to be a horizontal shift.
That's correct, Elijah. So we're not going to look at right now anything for a minute with anything inside the parentheses. So right now we're just looking at outside the parentheses. So if we're adding some constant to our trig function and it's not inside the argument, then that's going to shift it up or down. So let me just put this in real quick. So normally, here's our x-axis. But because of this midway line, let's shift everything up 2 units. And I'm just going to put this dotted line in here. This is just going to help me graph things. I wanted green. So I'm going to treat this dotted line as the place where it was going to cross the x-axis originally, if I hadn't shifted it up. So think of this as the midway line. So if our amplitude is 3, that means we go up 3 from that line and we go down 3 from that line. So if I go up 3 from 2, that's going to give me 5 as my max. So from here, because of my shift, the maximum value I'm going to get is 5. And the minimum value that we get, so if I go midway line is at 2 and I subtract 3 from that y value of 2, I get back -1.
Wait, can you go over that? I did not understand how you got the maximum and minimum.
Yeah. So normally to get max and min, we started at our x-axis or 0, y is 0, and we would add our amplitude and we would subtract our amplitude from it to get the max and the min. But because we shifted everything up 2 units in this case, when you look at the max and min, look at that y value where that midway line is and add your amplitude above that and subtract the amplitude from that. So
Okay.
when we found our amplitude was 3, so if we added 3 from 2, we got 5. And if we subtracted 3 from 2, we get -1. So I know my highest point that graph is going to reach is 5, and the lowest point that graph is going to reach is -1. Negative tells me here, because it's cosine, this is going to start at the min value. Because that's negative and it's cosine. If that had been sine, we'd start at not the origin, we'd start at the midway line. So we still haven't broken this up and figured out the period, so we need the period. So let's sandwich our argument between 0 and 2 pi. So 0 is less than or equal to pi fourths x, which is less than or equal to 2 pi. So our goal is to get x by itself. So I need to get rid of the pi fourths in front of the x. Think of it as we can multiply by the reciprocal. of that pi force. So if we multiply every single term by 4 over pi, that would make that coefficient in front of x1. So well, 0 times anything is 0. And this is less than x, which is less than, the pi's cancel here. And we have 2 times 4, so this gives us 8. So 1 period, our period is equal to 8. So 1, 2, oops. So let's figure out our important points. So we got to start, which is 0. We got an end value of a period, which we know is 8. So halfway between that is 4. Our quarter mark is the halfway between 0 and 4, which is 2. Our 3/4 point is the halfway mark between 4 and 8, which is 6. And so our important points are 0, 2, 4, 6, and 8. Okay, so again, it's cosine, so we start our max or min, but it's a negative in front of the coefficient, so we start at our min. So we're going to start at this point at 0, -1. At 2, we're going to hit our midway line. At 4, we're going to hit our max. At 6, we're going to go back and hit our midway line. And at 8, we're going to hit our minimum, which was -1. So it pretty much follows what we were doing, except that vertical shift. Just think of that midway line as what it would have been like the x-axis, where we would hit it on one of those points or multiple of those points. You want a sine or a cosine? What if it was y is equal to 5/3? Oh. Oh well. Sine of -2 pi/3 x, and then let's say plus let's just change that 5/3. I'm kind of coming up with one on my own. I don't know, let's make it a 2. And let's subtract, because we added already. Let's subtract 1. Okay. So because of the -1, we're subtracting a constant. This tells us that we're shifting down one. And so our midway line, we're going to treat as y equals -1, that horizontal line. The 2, this is our amplitude. And that will help determine what our max and our min is. Well, if we start at -1 for our y, To get the maximum value, we're going to go up 2. So if I went up 2 from -1, I would get back y is 1. And my min value, if I subtracted 2 from -1, would give me -3. And now I just need to figure out what my period is. Okay. So we can do this the same way. 0 is less than or equal to -2 pi thirds x is less than or equal to 2 pi. Okay, you got to be careful because if we multiply by a negative number and we're dealing with inequalities, that flips our inequality signs. And in order to get that -2 pi thirds outside, we don't want that anymore in front of the x, we're going to have to multiply by a negative. So we're going to multiply everything through by the reciprocal of -2 pi thirds, which is -3 over 2 pi. And so 0 times anything is 0, but we're changing the direction. It's greater than or equal to x, which is greater than or equal to, well, 2 pi's cancel, notice, and we're left with a -3. Usually I like to see things smallest to largest, and so let's just rewrite this. This is the same thing, we just need to be careful, make sure our inequalities are facing the correct way. -3 is less than or equal to x, which is less than or equal to 0. So we actually have a start at -3. And our end value of a period is at 0. The halfway mark, well, if you add those two together and divide by 2, -3 plus 0 is -3. So this would be, oops, just -3 halves. The quarter mark, this is where it might be helpful. We have to add those two together and divide by 2, or think of it as multiply by 1/2. So we have 1/2 -3. I notice I'm going to need a common denominator in order to add this. Let's just put 2 over 2 here, plus -3 halves, or -3 halves. So this is -6 halves minus 3 halves. That's -9 halves times 1/2. So 1/2 times -9 halves. This is equal to -9/4. And same thing, 3/4 point, probably harder to do in your head. Actually, it's not bad because of the 0. But if we added -3 halves plus 0 and multiplied by 1/2, this gives us -3/4. So I'm just gonna move it so that my x-axis gives me more room to plot on the right of it, or left of it. And we have -3. We have -9/4. We have -3/2, -3/4, and 0. Okay, so we're starting at -3. It's sine. Sine normally starts at the x-axis, but we're shifted down. So we're really going to start at -3, -1. Sine then normally goes upwards. And so we're going to hit our maximum point, because this is positive in front. We're not going to go down. Our maximum point, we said, was when y was 1. So at -3/2, you come back down and hit the midway line. -3/4, we're going to hit our minimum, which we said was -3. And then back at 0, we're going to hit our midway line. And so we've got one graph or one cycle of that. Okay, so you should be able to go backwards. So let's say instead of given the equation, you're given the graph and you're asked to find the equation. Well, we can kind of put it together like this, how we were doing it, bits and pieces. So we can locate what the max is, what the min is, and from there we can figure out what the amplitude is. We could figure out what the argument is by looking at the period of the graph. So let's say you're given a graph. Okay, on here, 1, 2, 3, 4. We have max and min. Max is 4, min is -4. We have 2 pi, 4 pi, 6 pi, 10 pi. We're on the origin. We're going upwards. At 2 pi, we hit 4. Come back down. At 4 pi, we hit the x-axis. At 6 pi, you're hitting -4. 8 pi, back up to the x-axis. 10 pi is at 4.
Professor,
Yeah.
how do you know when to hit the x-axis again? Because in the other one we didn't.
So we're treating that midway line like the x-axis. So if there's a shift up or down, treat that midway line like it was the x-axis. That's where it was going to cross at that point and point.
Okay. Thank you.
Yeah. So you're given the graph. You might be given more than one period. This is the graph is given. Now find the equation. So remember we kind of talked about these were sinusoidal, and I didn't even know if I pronounced it right, curves. So technically, these graphs could be written in terms of sine or cosine. It's just there's shifts in there. So it doesn't matter. I mean, someone might be able to write this equation in terms of cosine, someone in sine, and they get the same graph back. But looking at this, I would determine, or I would choose, because I have a point at the origin, that looks more like a sine to me. So I would choose a sine function because of that. I notice we have a max is equal to 4 and a min is equal to -4. The amplitude, that was equal to the max minus the min value divided by 2. Well, if I looked at this, this is equal to 4 minus a -4 divided by 2. So 4 minus -4 is 8, divided by 2 is 4, which you probably could have noticed by a max and min here. But sometimes if it's shifted up, it might be harder to see. So this is the process you would do that. And then we need to figure out what the argument is. So normally, we need to figure out what B is. Let's see, how do we do this? So notice that the period before we said was in the form of 2 pi over B. Right, we had sandwiched it in between 0 is less than or equal to B, X is less than or equal to 2 pi, and we got the X by itself, and we divided everything through by B and got that. And so knowing that fact, we know in this case that our period, so looking at when it starts repeating itself, well, starting at a 0 and repeating itself at, looks like at 8 pi, right? So we know that one period, that length is 8 pi. So we need to figure out what B is. So we have 8 pi is equal to 2 pi divided by B. Get B by itself. Well, let's multiply both sides by B. Fraction cancels. We're left with 8 pi B equals 2 pi. Divide both sides by 8 pi to get B by itself. Well, the pi's cancel, and this reduces to 1/4. So we know B is 1/4. We know A, depending on which direction it's going, we're starting and going upwards. So I know my A value is +4. And we decided to use sine. So putting that together, we have our equation. Y is equal to A, which is +4, sine of bx, so 1/4 x. So given the graph, we are able to get the equation.
Wait, how did you know to use sine again?
We could have used cosine, but that would have been a shift left or right. And so I didn't want to do that. And so noticing that the original graph, there was a point at the origin 0, 0, that told me that that looks more like a sine function. Where if that graph had started at 0, 4, like the maximum point, then I would have used cosine.
Okay.
Other questions? Okay, so we're looking at what you need to know for tomorrow's exam. You should be able to go back and forth between degrees and radian measures. So for instance, if we said convert 15 degrees to radians, you should be able to do that without a calculator. And so degrees to radians, recall, you multiply by pi all over 180. We can reduce this. So if you don't see how many times 15 goes in there, you can do long division. You can break it down into littler pieces. Like I know 3 goes into 15 5 times. I know 3 goes into 18 6 times. So this would be 60. 5 goes into itself once. 5 goes into 60. Well, 5 goes into 6 once with a remainder of 1. And 5 goes into 10 twice. So that would be a 12. So we would be left with 15 degrees is the same thing as pi 12ths radians. And then you should be able to go the opposite direction. So maybe we have a negative 5 pi halves, and it says convert to degrees. So instead of multiplying by pi over 180, it's 180 over pi. Things start reducing, pi's cancel out, and 2 goes into 180 90 times. And so we're left with negative 5 times 90. Negative 5 times 90 is equal to negative, well, 5 times 9 is 45 plus the 1 0 it ends with. So negative 450 degrees. You should be able to find reference angles.
Excuse me, Professor.
Yes.
The 450 degrees would be considered a clockwise degree, right? Correct?
Yes.
'Cause it's
So
negative.
you should be able to graph the degrees and radians. And so you're right. So negative would tell us that we're going clockwise. You should be able to tell me what quadrant that falls in. So here I know a full rotation is negative 360. And so thinking to myself, how much more do I need from 360 to 450? I know I need 90 more degrees. So that would get me to this negative y-axis.
Okay.
And so because it doesn't lie in a quadrant, what is the angle called? Anyone remember?
Quadrantal angle.
Right, so it's the quadrantal angle. So if it lies on the x or y axis, the terminal side, then it's a quadrantal angle. You should be able to also find reference angle. Well, this doesn't really have a reference angle because it's a quadrantal angle. You should be able to find coterminal angles. So there's an infinite number of coterminal angles. So am I asking you to find one of them, or maybe the formula that would get you any of them? So for instance, if I wanted the coterminal angle of negative 450, one of them would be, right, if I went clockwise, just 90 degrees. So negative 90 degrees in this case is a coterminal. I could have gone counterclockwise, and if I had gone counterclockwise, that would have been 270 degrees. But basically, if we take the angle we have, negative 450 degrees, and we add some multiple of 360 degrees times k. K is an integer. Would get us any coterminal angle.
Professor, I had a quick question about reference angles.
Yes.
Regarding reference angles, they always have to be acute, correct, to find the actual degree that is needed to complete it to be either 180 or 360, right?
Exactly. So it has to be an acute angle, and there, so that's between 0 and 90 degrees.
Okay.
So it's always positive.
And for coterminal, what's the difference with that?
The coterminal is any angle that would get us back to it. The reference angle is the angle that we're going to use, we could use to determine what the trig function is, and that would be in different quadrants, depending on what quadrant you're in.
Right. Yeah.
And it's always formed with the positive or negative x-axis, whatever one is closest.
Okay.
There's only one reference angle where there's an infinite number of coterminal angles too.
So does that mean you can have either or answer, like 270 or negative 90, or is it, how does that work?
So for a coterminal, that would be either or. So unless they put some sort of restriction on it. So they might have said, find the smallest positive coterminal angle. And then I would have said that was 270.
Okay. I also wanted to remind you, I don't know if you wanted to do this because you said you wanted to have everybody try their webcams out today. I did miss the first couple minutes of class. I didn't know if you said that already.
Yeah, I do want to do that. So I'm going to leave the last maybe 15 minutes of class to make sure you guys can get in okay and have no problems. Okay. So there are things that you need to remember. There were cofunctions. So remember, we could say that cosine of A, that was the same thing as sine of 90 minus A. Or sine of A is cosine of 90 minus A. Same thing with tangent and cotangent. So tangent of A is the same thing as cotangent 90 minus A. Secant A is the same thing as cosecant of 90 minus A. And so those were sometimes helpful when we were evaluating certain trig functions. Maybe we didn't know what they were at. Let me see.
Does the A have to be in degrees?
No, not necessarily. So this could have been, yes, if it was written like this, yes. So this is equivalent to, it could have been in terms of radians before. So if we were looking at radians, we would treat it as pi halves minus that angle. So depending on what you're looking at, radians or degrees.
Professor, what's the official name of the points on the unit circle, like square root of 3/2 and 1/2 points? What are those called? Do they have a name at all or anything?
Those are just those are the special points that we need to know because they're at the special angles.
Right.
But I don't know, I haven't heard of them being called a particular special name for those.
Okay, thanks.
So what if you had sine of negative 40 degrees all over cosine of 50 degrees? And it told you to evaluate this without a calculator. So these are actually angles that we do not know. And so there must be some way that we can manipulate this.
Would you change them into radians?
So but changing them into radians isn't going to help us because those radian measures we don't know either.
We could use the cofunctions above.
Yep, so using the cofunctions above. And we also could use the fact of odd and even functions. So recall that sine was an odd function, meaning that sine of negative theta, this was equal to negative sine theta. So we could use that fact. So we could rewrite this as negative sine of positive 40 degrees all over cosine of 50. And like you said, using the cofunctions above, so either rewrite sine in terms of cosine or cosine in terms of sine, it doesn't matter. By the cofunction above, but maybe let's just do sine. Well, we know that sine of 40 is equivalent to cosine of 90 minus 40. Maybe I'll just write it here. All over cosine of 50. So this is negative cosine of 50 over cosine of 50. So this is equal to negative 1. So what about sine of 400 degrees secant of negative 50 degrees? So again, it's asking us to do this without a calculator. So I see secant, I don't like that. So we could rewrite that in terms of sine or cosine, depending on what secant is. So secant is, it starts with an S, so it's 1 over the trig function that starts with the other letter, so cosine of negative 50 degrees. This almost kind of looks like the same thing. Let's find a coterminal angle to 400. So let's graph 400. That is 1 full rotation, right? That's 360 degrees. So we need 40 more degrees to get up to 400. So it's equivalent to sine of 40 degrees. This is all over cosine of negative 50 degrees. Multiply fractions, multiply straight across. Cosine is an even function. So that tells me that cosine of a negative angle is equal to cosine of that positive, the opposite sign of that angle. So this is saying this is the same thing as cosine of 50 degrees. And then again with cofunctions, so we can say this is the same thing as sine of 90 minus 40 all over cosine of 50. So this is equal to oops, I meant to say cosine of that. So this is cosine of 50 over cosine of 50, which is 1.
Professor, I had a quick question.
Yeah.
So if the negative hadn't been with or inside the parentheses with the 50 degrees, if it was outside of cosine, would it still be an even function?
Well, yeah, but you would have to, it's still an even function, yes.
Okay, thank you.
It's just that negative is just reflecting it across the x-axis. And it would still give us the same value. So if this had been like negative cosine of negative 50 degrees, this would be the same thing as negative cosine of 50 degrees.
Professor,
Uh-huh.
what happened to sine 40?
Sine 40. Sine 40, I was using the rule that it's a co-function to cosine. And so sine 40 is the same thing as cosine of 90 minus that angle. So I was trying to manipulate it so that what was in the numerator denominator was exactly the same so we could evaluate it.
Okay.
Professor, I'm still having a little bit of a trouble understanding why the cosine is even. It's not odd.
A couple ways to think of it. If you're looking at the unit circle, you can kind of think of it that way. Cosine again is our x value on the unit circle. And so if we think of this as theta, right? We have some point here. This is our x. This is our y value. And we go the opposite direction, right? And so let's say we go negative theta. That would get us in the fourth quadrant. So this point right here is going to lie here. So notice that the x value, negative theta. So cosine of theta here is equal to x, but cosine of negative theta, it's still the x value over your point is x. And so since cosine of negative theta, by definition of even function, is equal to cosine of positive theta, this by definition is even. Where sine, notice that point changes. So when I look at the negative theta, my y value is now negative y. So sine of theta is equal to y, where sine of negative theta is equal to negative y, which is the same thing as multiplying negative sine theta. And so by definition, this means it's an odd function. The other way to think about it is looking at it graphically, not on the unit circle. Even functions are actually symmetrical across the y-axis. So it's a little confusing when you're thinking of the unit circle. And if you looked at your cosine function, remember it started up here. And so if we folded our paper across this y-axis, it's symmetrical, where this is cosine. Odd functions are symmetrical across the origin. So basically folding your paper into fourths would give us a mirror image. Oops. And this is what our sine function looks like. And we folded this in fourths, it'd be a mirror image across.
So it's like a mirror effect, correct?
Mm-hmm.
Okay.
And so just knowing those rules just kind of helpful for, taking out the negative front or making it, or not, just looking at positive angles and determining, do you need to pull that negative out front or does it just go away? Are they equivalent?
This was on
Should we
chapter 2,
memorize? Sorry.
If you know that cosine's even, sine is odd, then the other ones come out really easily because you can rewrite the other trig functions in terms of sine and cosine. So if you guys were given sine theta is equal to negative 5 over 13, you're given that theta is contained in quadrant 3. Actually, no, it says quadrant 4. You should be able to find the remaining trig functions. So think about sine and what you know about the relationships of sides of a triangle. Sine is the opposite theta all over the hypotenuse.
Excuse me, Professor, I have a question.
Huh?
So does it matter which one is the negative number? So because you could write it as like -5 or like -13.
Technically, I actually kind of treat it with the numerator. I usually don't even like to think of it as that, but the radius is always like a positive.
Why is sine of theta going to be in quadrant 4, not quadrant 4 or quadrant 3? Like,
You're right. It could, if it was negative, it could be in either. And I'm just now putting it in quadrant 3, which it's not. But it was defined. We need to know what quadrant it's in order to figure out what the other trig functions are.
oh, okay.
Because depending on what quadrant we're in depends on which trig functions are positive and negative. Okay, so I know I'm in quadrant 4. The 13 is my hypotenuse. My theta is always with the x-axis. So this is theta. And I have this triangle. So think of it opposite of theta, and theta is always with the x-axis. That was my numerator. So this is -5. I do not know what this length of my triangle is. And that's where we can use the Pythagorean theorem. I tend to not like to put -5 there. I tend to like to just say, well, this is just +5 because I'm looking at a triangle, and then I go from there and determine is my function positive or negative. But technically, if you leave that as -5, it will help you when you do the ratios. You don't have to even worry about is it positive or negative. So it's up to you how you want to look at it. But I'm going to find this value here. Maybe let's call it x. So I know that x squared is equal to my hypotenuse squared, 13 squared minus 5 squared. So x is equal to the square root of 13 times 13 is 169 minus 5 times 5 is 25. So this is the square root of 144, which is 12. And so from there, you should be able to get the other 5 trigonometric functions. You guys good with that?
So here you don't use the Pythagorean theorem.
We did to figure out what this side was, because we were given 2 sides of making it. We knew 2 sides or lengths of the triangle, but we didn't know one. And so now we would say, okay, well, cosine then of theta. Well, that's opposite. I'm sorry, adjacent, which is 12. All over hypotenuse, which is 13. Cosine is positive. I don't have to put the positive, but I'm going to just to enhance that it's positive in quadrant 4. And then I know that the reciprocal function, which is secant, that would be 13 over 12, and it's also positive. I didn't even need to do work really to find cosecant. So cosecant theta is the reciprocal of sine. So that would be -13 over 5. Tangent theta is opposite. So -5 over adjacent, 12. Cotangent is the reciprocal, so -12/5. Okay, so given what a trig function is, you should be able to find the other trig functions, or given a point, you should be able to find the 6 trigonometric functions. So I'm like that.
Professor,
Mhm.
how'd you know that 5 was the negative one and not 13?
Yeah, you know, so I'm just using the fact that if you have a negative in a fraction, you can have it out front of the fraction. You can put it in the numerator of the fraction, or you can put it in the denominator of the fraction. They all mean the same thing. As long as you don't put it both in the numerator or denominator. So that's why I'm doing that, but they're equivalent. The only reason why I said not for the hypotenuse, that normally you don't see it, is because if we're thinking this as points, then our y value, notice that length, that y, to get to that point, our y value is -5. So this really would have been at the point 12, -5.
Excuse me, Professor.
Mm-hmm.
On the x squared equals 13 squared minus the 5 squared.
Yeah.
How do you do that? Can you tell me step by step? Because I've seen different ways to do it. Because I seen they cancel the square on both sides, and then the 13 the 2 on the 13 it disappears, and then you just have to square the 5. I don't know. I was kind of confused. Can you just?
That's actually wrong.
Okay.
So order of operations, you have to first treat this radical as a parenthesis. So you would have to, when you took the square root of both sides, to get x by itself right here. Order of operations, we have to do exponents first.
Okay.
Then we have to do subtraction. So we're treating this like a whole parentheses under here, working inside the parentheses. So we cannot take that square root until after we've done all those operations under here. If it had been multiplication, I could do it where I could break it down. But if I have addition or subtraction in between my squares, I have to wait until I get that as a single number before I can take the square root of it.
So I have to square it first before I take them away. Okay.
Yeah.
But the x you can just take away because there's nothing there, right? It's just a 1.
Right. The square root of a, yeah, it's just one term. So square root of x squared is just x. Exactly.
Okay. Okay.
So basically, you guys should have been able to, and I'm not going to go over it, but if it had given you that point, it would have said instead, you know, find the 6 trigonometric functions given at the point 12, -5. And so you would have plotted your point, and then you would have made your triangle and done what we had just done.
If it was in that the find the point terms, would it also say like it's in quadrant 4?
No, because once you plot the point, you should know what quadrant it's in, right? Because you would have gone over to the right 12 and down 5 to get to that point, and I would have known that point then lies in quadrant 4.
Okay, gotcha.
Let's see. Just trying to pull stuff out that I see is good. Let's see, let me go back. Where did you guys have that trigonometric identity? Cosine squared plus sine squared equals 1. What that was.
That was 7.2, right?
Was that 7-2? Thank you.
Chapter 2. Like the middle of chapter 2.
Awesome, thank you. Okay, so you should be able to use your Pythagorean identities to evaluate trigonometric expressions at values you don't know. So for instance, let's say we had 1 minus cosine squared of 15 degrees. And I might have done this before, I apologize if I have, minus cosine squared of 75 degrees.
You said we're going to have a reference sheet for these trigonometric identities or no?
No. So basically you can, as long as you know this one, cosine squared theta plus sine squared theta equals 1. You should be able to quickly drive the other ones. And so when I say quickly, so if I divide every single term by cosine squared in here, that's going to give me my other one. So cosine squared divided by cosine squared, that's 1, plus sine squared over cosine squared, sine over cosine's tangent squared, theta equals, and 1 over cosine squared, well, that starts with c, so it's a secant squared theta. So that's how you get the other one. Start with this trigonometric identity and divide everything now by sine squared. Well, cosine squared over sine squared. Cosine over sine is cotangent, so that's cotangent squared theta. Sine squared over sine squared is 1 equals 1 over 1 over sine squared, which is cosecant squared. And then you can get any type of form from here by, moving things over to one side of the equation. So I know like sine squared theta is the same thing as 1 minus cosine squared theta.
So we use the reciprocal identities to create Pythagorean identities off of 1. And do we use quotient identities as well for the tangent and cotangent?
So that's what I'm using. So I'm just dividing everything through by cosine squared in one equation and using, the fact that tangent, all these other trig functions could be rewritten in terms of cosine and sine to get what trig function they are.
And there's only those 3 Pythagorean identities?
Yep.
Okay.
But you should also recognize the different forms of them like that I was saying.
Sure.
So, so once if I was doing this, I might write this down right away and write these down if I was looking at problems like this so that I could identify really quick what they look like. So like right here, I see cosine squared and cosine squared. I know I don't know those values, but I also know that I can manipulate it. I notice 90 minus 75 is 15. Or 90 minus 15 is 75. So I can manipulate this one to be a cosine squared, sine squared type in here. And then I can manipulate that to look like 1. So I know that this, let's see, let me just do minus real quick. This right here is the same thing as sine squared theta, sine squared of 90 minus 75 degrees by being a cofunction. So now I have 1 minus cosine squared of 15 degrees minus sine squared of 15 degrees. To me, that almost looks like this. If I factor out a -1, I can manipulate it to look like that. So I have 1 minus, factor out a -1 from the trig functions. I have cosine squared 15 degrees plus sine squared of 15 degrees. But that's just 1. And so I have 1 minus 1, which is 0. Okay.
So Professor, I've been told that the 3 best things to memorize for this test is the unit circle, the trigonometric identities, as well as there's like a chart table that tells you the quadrants. I've seen it in the homework regarding like quadrant theta 1, 2, 3, or 4, and then which one goes into.
Right.
So I just was wondering, is there any other like things you think we should really study besides those three top things?
Be able to do a couple word problems involving right triangles. And then also, we looked at the area of a sector, or we looked at the arc length.
Everything on chapter 1.
Yeah, and this was S. This length, S, was equal to R times theta. R had to be in terms of radians in order to use this formula.
Oh yeah, of course.
And then we also had degree, minute, seconds. If I did one of those, I would just give you one of them. What else do we have? Angular and linear speeds. So that was how fast is your point moving along, rotating, or how fast is this angle moving as we're rotating?
Professor, can you tell us the difference of angular and can you tell us the difference of both the speeds?
The linear speed, think about it's the point and how fast that point would be moving. So if I was on a wheel and I want to know how fast I was going around on that wheel, that's the linear speed. Angular is how fast is that angle rotating, and not the point out here.
Okay.
Those are both equipped with their own formula for solving that, correct?
Yeah, and so I quickly kind of do it by knowing that distance equals rate times time. They use, they don't use D and they don't use R because of different reasons. R we kind of look at as radius. They use V and S. So the distance S, because we looked at this as S, is equal to V times T. And so if I want to get velocity, speed, I would divide both sides by T. So my linear speed is V is equal to S over T, where S, remember, is R times theta. So that's linear speed. Angular speed, we're looking at the angle. And so, what is it? They used omega. That was equal to your angle. How much are you swiping over the time? And that was our angular speed.
What was the area sector formula? It was like A equals 1/2 R. I forgot the rest though.
I think it was pi r squared. I don't actually know that one. Yeah, it was the area of a sector. So if I wanted to find this area in here, that was 1/2 times pi r squared theta. Oops, there's no pi. It's 1/2 r squared theta. My computer's starting to freeze. Come on. Okay, so I think this is a good time to stop. There we go. Let me pause, or let me stop the video.